Greetings. Welcome to the module on making data accessible, discoverable, and useful. This is part of a series where we introduce data science in the context of engineering and physical science applications. I'm Alejandro Strachan, professor of materials engineering at Purdue University. And in this module, we'll discuss fair data principles, how you can use your data to accelerate innovation in the field. We'll learn about open repositories where you can share your data, including metadata, with your community. And there's a homework assignment where you'll be able to explore one of these repositories and learn how to how to contribute your own data to such resources. I talked a little bit about the learning objectives. We'll learn about FAIR principles, how to add data to describe your results so that your results can be put in the right context and your data can be reused. And we'll discuss how to contribute your own data to some of these repositories. And these FAIR principles, FAIR is findable, accessible, interoperable, and reusable. These principles apply not just as data as most of us understand, but also to models and scientific workflows. So we'll discuss how you can share these models and workflows with your community. So all of this is part of data science. And data science aims at learning from data by example without underlying or without the need for knowledge of the underlying physical laws. And of course, an important aspect of data science is you have to start by acquiring data and know how to handle data. The flip side of this coin is that this data needs to be contributed, and people in our community needs to share their data and make their data findable and accessible and useful. So once you have your data, you can use the data to train predictive models. We have modules on that in this series to develop machine learning, to develop neural networks or random forests. There's a field called unsupervised learning that seeks to find patterns in the data, the underlying structure of your data. And many of the things can be put together in design of experiment efforts where you use the knowledge that you have on predictive models to determine what is the next experiment you should carry out to achieve your design goal. So in order for these data science activities to occur, we need an underlying cyber infrastructure to support the data and the models and allow people to find data and share, contribute their own data. And throughout the series, we used several modern infrastructures to do our activities. And in this particular learning module, we'll use Citrination from Citrin Informatics and nanoHUB as the two resources to share data and share models. So why is this important? Well, generating data in our field is time-consuming and expensive. And what happens currently is that the majority of the data that our community generates dies in researchers' laptops. A small fraction of the data makes it into a publication, but even that small fraction of the data is not discoverable. It's hidden maybe in a table or in a plot that's not machine readable, and it's certainly not queryable. And so that really stifles innovation, because finding data from which you can train models is a very labor-intensive effort, which shouldn't be. And so we're going to learn how the importance of sharing data, including metadata, that tells us about the provenance of that piece of data. And the benefits are that it would really accelerate innovation. People will be able to build on your results quickly. Maybe results that are not useful for your own publication are useful for someone else that's interested in a different topic. In the last few years, a set of principles evolved. They're called FAIR data principles that aim at making data findable, interoperable, accessible, and reusable. And so for the data to be findable, they need to have a unique identifier. You probably are familiar with DOIs, digital object identifiers, and the data should be searchable. For the data to be interoperable, it needs to use a representation with a language that's formal and accessible and broadly adopted. For the data to be accessible, it needs to satisfy protocols that are widely used and they're easy to implement so that others can access your data. And for the data to be reusable, it needs to be include a rich metadata that describes how the data was generated, the provenance of your material. And that guarantees that with this full context, other researchers, and more importantly, automated systems, would be able to assess whether the data that you collected for purpose A could be used for purpose B and reused and benefit others and accelerate innovation. Here's a paper published on the journal Scientific Data about FAIR principles. The paper is an interesting read, and I would suggest it to everyone. It's not written for experts, and it's not about the details of the implementation, but the general principles that all of us can start adopting. In the paper, they go into a little bit more detail into findable and accessible and interoperable and reusable, and how all of these apply both to the data and the metadata. And also the importance of putting enough information in systems so that automated systems, computer programs can make decisions about the data, what data is useful for them, what data isn't, about access to data, about the permissions to reuse the data that has to do with licensing. All of that needs to be taken into account. And I think it's important to highlight that you don't necessarily need to adopt all of these principles all at once and to the highest degree, but you can start using them in your own work and adapt them as you can and in a progressive fashion. So let's talk a little bit about metadata. So the metadata is critical for reusability. And the metadata describes the context in which that the result was generated, and it seeks to provide a complete provenance of your data. So these are examples, what you see there on the little pictures on the right, of computational data that shows a calculation on iron oxide. And there's a bunch of properties that were calculated computationally, but there's a lot of other data that is not there's a lot of other entries that are metadata. It's not the actual output data, but it tells you how the calculation was conducted. It tells you, for example, an energy cutoff that has to do with the details of the calculation. What type of symmetry was applied? What type of constraints, symmetry constraints were applied to the simulation? K-points. So these are important aspects of the calculation that affect the result. And with knowledge of all of these, an expert can easily reproduce the results or assess how that result was obtained. This is a computational example, but of course the exact same ideas apply to experimental data. So the resources, the number of resources available in the material science community for data and models has grown very significantly over the last decade following the Materials Genome Initiative in the US and other similar efforts around the world. The Materials Resource Registry shown here is a resource by NIST, the National Institute of Standards and Technology, and they list, it's a registry of resources, so you can go there and find the resources, the infrastructure that might have the data that you seek. So it's a very useful resource. So let's jump into an example, and let's say you're convinced and you want to share your data with the community. One platform that allows you to do that is called Citrination. It's by a company called Citrin Informatics. It's a repository, but they also have a lot of artificial intelligence, machine learning tools to work with the data. And the steps to contribute your own data to Citrination are really simple. You start by selecting a template depending on the data that you have. So if you have NMR data, or if you have maybe crystallographic data, you provide a CSV file. There's more general type of data formats like a CSV, comma-separated values input. There's Quantum Espresso or VASP. These are electronic structure calculations code. So you pick your template, and then this is the example if you want like a CSV or Excel type template, and you use keywords to tag your data and your metadata. And this set of keywords allow Citrination to organize their data in a coherent manner. So this is an example of a data that was collected by a student in my group, Juan Verduzco, who spent months combing through the literature, searching for lithium-ion conductivity measurements of a set of oxides that we're interested in. This is his file, his CSV file. And what you see is there's, of course, the composition, the property that we're interested in, but a bunch of other descriptors. For example, at what temperature was this ceramic sintered? Because that affects the porosity, and the porosity affects the measured ionic conductivity. What is the measuring temperature? What crystal structure was the structure? These oxides called garnets can crystallize in a cubic or a tetragonal phase, and the ionic conductivities are very different. So preparation, not just the result, but as much metadata as you can. And of course, this is done a posteriori from a set of papers in the literature. When you're carrying out your experiment, you have access to all of the metadata required to reproduce the results, and you should collect those. And so once you have the data, you go to Citrination and you pass it through an ingester that takes your data and generates this little information. It provides a DOI, digital object identifier, and here's your data. And anyone from around the world can learn from your data, query your data, find it, filter it, whatever they need to do. Now, we talked about the fact that it's important to share not just data, but workflows and models. So research involves almost always complex workflows that involve several steps. You collect data, you perform an analysis, that's an output data, and then you do something else to that data. And these workflows are often not shared and poorly explained in publications. So even for experts, reproducing the results in a publication can take months because there are gaps in these workflows. So sharing workflows, sharing the entire analysis can really accelerate innovation in our field. And we have the technology to do it. Jupyter notebooks are a tool for interactive computing that combine rich text, powerful visualization, they run on your web browser, and live code. So they're becoming the tool of choice to document scientific workflows. So if you develop your own Jupyter notebook to analyze your data, and I think that's always a good idea, whether it's experimental or computational data, then you can share your Jupyter notebook with your entire workflow analysis with your community so others can build on it, they can reproduce your results. You can do it in repositories, a Git-like repository, GitHub or some other repository, but you can also publish your notebook in nanoHUB. That's an infrastructure for online simulations supported by the US National Science Foundation. The interesting thing about publishing something in nanoHUB is that folks can run it actually in nanoHUB using cloud computing from any standard web browser. So it's, in my opinion, an attractive avenue. So let me show you some examples. This is a workflow that uses a set of simulation tools to predict the glass transition of a polymer. Okay? So you start by selecting a monomer, use a tool called Polymer Modeler to build a polymer chain and pack it into a simulation box. You can visualize the structure right there in Jupyter. And then you launch a molecular dynamics simulation using a code called LAMPS to run a simulation with this model that you just created and move all the atoms. And to extract the glass transition temperature, we would run a simulation where we start at high temperature and we cool down the system across the glass transition temperature. And so if you plot the density as a function of temperature, like what you see here, the glass transition temperature is given by this changing slope. And so this workflow generates the raw data from the molecular dynamics simulation, and it also post-processes the data to extract the actual number, the glass transition temperature. And it does so using two different methods, and it reports two different glass transition temperatures. So the whole thing is documented, from building the model to running the simulation to post-processing the result. Everything is in the same notebook, and once you're done, you can publish it in nanoHUB. It is containerized, so this workflow will always run the same way. Anyone can run it, reproduce our results, and they can also modify it to fit their needs. This is another example of a data science workflow that uses active learning. So here we query materials data to get our initial data, we develop models, and then we use active learning for design of experiments. If you're interested in active learning, there is an entire module devoted to active learning in this series, and I would encourage you to go ahead and do it. And once you're done, you plot your results, and again, everything is documented in a single notebook. These are two examples of end-to-end scientific workflows for data science that are available in nanoHUB. Anyone can run them, anyone can modify them, and build on them. So before we finish, I wanted to give you some resources if you're interested in getting started with creating Jupyter workflows. You can use nanoHUB to do that. If you go to nanohub.org/tools/Jupyter, you can launch a Jupyter notebook right there and start coding. There are lots of pre-installed packages for machine learning, physics-based simulations, stats, visualization, whatnot. And there's resources on how and why to publish in nanoHUB, and the second link here in the middle is a presentation with details about developing tools in nanoHUB, using Jupyter and deploying those tools. Now, if you're a developer of physics-based simulators, maybe you have a tool that uses finite elements, or it's a device simulator, or uses molecular dynamics, we have a product called SimTools that allows you to wrap your tool with inputs and outputs that are declared, are accessible, and they satisfy FAIR principles. If you're interested in developing a tool like that, here's, if you go to nanohub.org/tools/intro to SimTools, you'll have a lot of information about how to develop and deploy one of these tools. So, in summary, we can really accelerate innovation in our field by sharing our data, sharing the data in ways that follow the FAIR principles. They're discoverable, interoperable, queryable, using modern tools. And this applies not just to data, but to models. And there are really lots of resources that can make this process relatively painful. And I hope this module gets you incentivized to start following these principles. And there's a homework assignment that where you will explore existing data in the Citrination repository. And I think that will help you understand how you need to organize your own data to contribute to this, to contribute your data to the worldwide materials repositories. Thank you very much.